So if I go and graph, say something like a half x plus 3. And I want to know, I'm going to zoom in a little bit, I'm going to think about what value is it approaching as x goes towards 2. So I write that as the limit as x goes to 2 of a half x plus 3. And so if I graph this function, a half x plus 3, okay, every y coordinate that lies on this line is the value of a half x plus 3 for a particular value of x. So when x is 2, the value of a half x plus 3 is whatever the y coordinate of this point is, so it's 4. But when I'm thinking about the limit, I'm saying the limit as x goes to 2. So as I go along here, as my x values are coming to this value of 2 right here, I'm saying what are my y coordinates approaching? So for that, if I draw an arrow along there, I'm saying what are my y coordinates of this point along the arrow going towards? What are they approaching? What are they going to be limited by? What are they going to get very close to but never go beyond? That's why we call it a limit, because they're going to get more closer to it, but they're never actually going to go beyond that value. And so I can do that from both ends. You see, I can come down. That sounds real creepy. I'm going to come down and I'm going to say, what are the values of the y coordinates as we come down that arrow? Because they should be both coming towards the same point. If they're not, we don't actually have a limit. And I might do a quick example of that at a different point. So we want to say, well, what are they coming towards? And because we can read off the graph, we can say, well, the y coordinates along both arrows are going towards 4. So we say the limit as x goes to 2 of a half x plus 3 equals 4. Surely that was a lot of work. I mean, isn't there another way of doing it? Well, we could say, what's the value of a half x plus 3 at 2? Because that's what it's going towards. So I can just substitute. I can go half, and I can put 2 in for x plus 3, and then a half times 2 gives me 1, add 3, that's going to give me 4. So the graph is a visual representation of what we're actually saying, what we're looking for. Substitution is an easy way to get it. So let's find the limit of a different one. Let's find the limit as x goes to 2 of x squared plus 2x plus 3. Now you didn't do this one on Friday for those that are in class, so I want you to actually do this one. Find the limit as x goes to 2 of x squared plus 2x plus 3. So if I jump back and I do the limit as x goes to 5, of 2x, x take 5 over x take 5. What happens when I substitute 5 into this equation? What do I get? Sorry? You're dividing by 0? What are you dividing by 0? So what number do I get in the numerator? I get in the denominator, I get 0, but what do I get in the numerator? So I get 0 on 0, which is even worse than just dividing by 0. So the issue is that substitution gives 0 on 0, which is actually downright meaningless. There is nothing, no number attached to 0 divided by 0. So then how do we do it? Well, let's go back to the graph. This is what the graph of 2x, x take 5 looks like. We have a spot missing here at 5. And the reason we have a spot missing there is because that value of the function is 0 or 0. It can't assign a value to that point. But does that matter? Does that mean that we don't have a limit? Well, no, it doesn't, because remember, we only care about what the values either side are approaching. So if you think about it, if I draw an arrow along there, along my function, on both sides, so one coming from above below and one going from below up, are they still approaching a real number? Are they still approaching some number? Yes, they are. We don't know necessarily what it is. Substitution doesn't give it to us. But they are approaching some number. Approximately, what is that number? 10. So this one coming from above below is going towards 10, and this one from below up is approaching 10 as well. Both are approaching some number, and so while substitution doesn't give us a valid answer, the limit actually still exists. There should be a valid answer. So what we do is we think about, well, this function, substitution doesn't give me the right answer, but let's use a function very, very, very similar. This is y equals 2x. What's the difference between 2x, x take 5 on x take 5, and 2x? What's the difference between the two functions? Let me just write them both out. So let's remind ourselves, this is y equals 2x, x take 5 and x take 5. And this is y equals 2x without the x take 5s. Are they exactly the same function? Is there no difference between the two? No, why not?
When x, the value of x equals 5, there is no y value.
Yeah.
While as in the second one, there's a value.
There's a value. The value is 10. Okay. Does that work for any other points? Are there any other points where they're going to be different? Is there going to be any other difference between these two functions? For any other value of x, you're going to get a different answer between the two. No, why not?
Why does the functions are basically the same, so that the first one is f and x equals 5 cancel y.
Yeah.
If you just factorize the first function, you get y equals 2x.
Yep, so if we cancel the x take 5s,
Yes.
we are going to just get y equals 2x. And so for any other x value, say if we put 4 into this function, so if I say y working well. Let's go back to this. So if I say y is equal to 2x, x take 5 on x take 5, and I'll work that out for any other value apart from 5. So if I say y is equal to 2 by 4, 4 take 5 over 4 take 5, we're going to get some number that's not 0 here and here that can just be cancelled. So I just get 2 by 4 times minus 1 over minus 1. The minus 1s would cancel and I'd get 8. So provided that these values aren't 0, we're just going to get some non-zero number that can be cancelled out, and it'll just give us 2 times the x value. So then, what am I saying? Well, the key point is the only difference between y equals 2x and y equals 2x, x take 5, and x take 5, the only difference is that point at 5. In one, it doesn't exist. In the other, it exists perfectly. That's the only difference between the two functions. See, what does that mean? What it means is a couple of really important things. The first thing that it means is that we can say that 2x, x take 5 on x take 5 is equal to 2x, provided that x does not equal 5. What we're saying there is, as long as we're not considering this point, as long as we're not considering when x is 5, these two are actually exactly the same. They'll give us the same number. As long as we don't want to consider that. That's the anomaly to this equation. It's the bit that doesn't quite fit. Why is that useful for limits? Well, let's jump back to our graph. You see, on the graph, we don't actually care what the value is at that point. Remember, we're talking about these arrows. We care what the y-coordinates along those arrows are, because it's the y-coordinates of those arrows that are approaching a point. So we're asking ourselves, what are the y-coordinates of these arrows approaching? That's what the limit is. It's not actually what the value is at that point. So what the y-coordinates of the arrows approaching is the same here as it is on this graph as well. You see, if I draw the arrows here, that's not going to work for me. But I've got 5 there. So the arrows, if I come along here, along this graph, the y-coordinates of the points along this graph as we're going towards 5 will actually be exactly the same as they were on the previous function. So we're approaching the same limit. We're approaching the same value, which actually means that we can use this idea to solve. So if I go back to here, and I'm just going to clean up some of this. So this is how we do it. So I can say the limit as x goes to 5 of 2x, x take 5 on x take 5. I can say this equals the limit as x goes to 5 of 2x, x take 5 on x take 5. And in this step, I can cancel out the x take 5s, provided that we're not going to think about when x equals 5. So then I get the limit as x goes to 5 of just 2x. But I know how to do this limit. This limit just happens by substitution. So because I can do that limit, I just substitute in 5, and the limit gives me 10. See, what I've done is I've taken a limit that I can't do by substitution and created a limit that I can do by substitution. You might say, well, you put 5 in down here, but we said x can't equal 5. Remember, it doesn't matter. Limits only care about what we're approaching, not what actually happens there. So because these two functions are exactly the same as we're approaching 5, the limit on 2x will be the same as the limit on this function. It's all about what we're approaching either side of 5, is not what is happening at 5 that we care about. So, if I go back to my Word document, we've got three limits here. And they're going to need something cancelled to be able to do them, because if you just do substitution on these, you're going to get 0 and 0, and that doesn't tell us anything. So what I want you to do is I want you to have a go at these limits, but you must cancel a factor on the top and bottom line first before you substitute. So I'm going to give you a little bit of time to have a go at these, and then we're going to, if I have the limit as h goes to 0, of 2h take 3h squared plus 4hx over h, that's going to equal the limit as h goes to 0 of h outside of 2 take 3h plus 4x all over h. The h's cancel. And by substitution, this is going to equal 2 take 3 times 0 plus 4x, which is just 2 plus 4x. Second learning. First learning was we can factorize. Second learning is a limit doesn't actually have to be a number, it can be an expression. Third learning. Let's try this last one. Limit as x goes to 2. Of x squared take 7x plus 1 over x squared take 4x plus 4. Now, in that case, I'm going to try factorizing again. So it's going to be a quadratic, so 2 factors, so x and x must be the first terms, and I need something that multiplies to give 1 and adds to give minus 7. That's why I can't do it. Let's try that. I was thinking there wasn't much, because the only thing that multiplies to give 1, positive 1, is 1 and 1, and minus 1 and minus 1. Neither of those are going to add to give us negative 7. So, thanks for rescuing me there. Alright, so 10. Let's try that. Okay, 5 and 2 multiply to give 10. We need negative 1, so it's going to be minus 5 and minus 2. And that's going to be all over x squared take 4x plus 4. Now, because you're all brilliant at factorizing quadratics, you all can recognize that that's x take 2 squared. So let's cancel out x take 2 and the squared. So now if I substitute 2 in, I'm going to get minus 3 over 0. Now, a couple of potential ways of thinking about this, but what the graph actually looks like is we have a vertical asymptote at 2, with the graph going up like that and down like that. Now, depending whether you come from the right or the left, you're actually approaching different things. So it's actually, you can't say that this is infinity, okay? You can't say that this limit is infinity, because is it negative infinity or positive infinity? It depends on which way you're going. So the only thing we can say is that this limit is undefined. Okay? Now, why would I make a difference and say that this limit is rubbish? Well, it's not 0 and 0, okay? 0 and 0 is complete rubbish, okay? This is just partial rubbish, if you want to think about it that way. It's only partly rubbish. Kind of got 1 foot in the bin and 1 foot out, whereas 0 and 0 is totally in the bin, lid closed, off to the dump, okay? So this isn't such a bad thing, but the limit is undefined. It's fine to say it's undefined. It happens. Okay? All right. Any questions about those? Yeah. Only if your space includes infinity or negative infinity, which normal real numbers don't. Because any number divided by 0 is either positive or negative infinity. Now, normal real numbers don't include positive or negative infinity. So for the real numbers that we deal with, we say it's undefined. If you want to give it a number, then you've got to bring negative and positive infinity into your number space that you're working with, and you can call it that, and then it has a definition. Okay? Don't worry too much about that. That's the basic answer though, if it's basic. If you've got more questions, feel free to ask me that. Okay. Now I'm going to think about rates of change. Rates of change is where we're going. That's what calculus and derivatives are all about, and that's why we need limits. So if I have a look at this red graph and this blue graph, which graph would you say is changing faster? If you want a way to think about that, if this was mapping the volume of water in a tank, so the volumes are going up, which tank is filling faster? Which has a faster flow into it? There's a faster increase. The red graph. What feature of that red graph tells us that it's got a faster rate of change? It's changing faster. Slope? And what about the slope? Sorry, it's great, it's higher. More slope, changing faster. Slope is all about how fast it's changing. And this one's going up quicker. It's got a greater slope. Therefore, its rate of change, we can say, is greater. Now, that's not so bad. And we could find these slopes. We could find these gradients, and that would tell us exactly how fast this graph is changing. Because you see, remember what it slope tells us. It says for going across one unit, we've gone up a certain distance. So for an increase in 1 in the x, we're going up a certain amount. That's what our gradient tells us. That's what we want from a rate of change. Remember, a rate is relative to an increase of 1, generally in time, but it doesn't have to be in this case. So for an increase of 1, we've gone up by a certain amount. If we're thinking about volumes in tanks, we could say for an increase in 1 hour, we've gone up by a certain volume. And we can see that the volume on the red graph will have gone up more in that time than the blue graph. Okay? So what about this one? See, what's different between the straight lines, the red and the blue graph, compared to this graph here, when we're thinking about rates of change and how quickly it's changing? What's the difference? Yep. Yeah. You see, let's go back to my volume. If I go between here and here, volume's only going up a very small amount. See, let's take a unit of 1 going across 1 hour and then up. My volume has not increased very much. But if I take a later time, my volume's actually gone up quite a lot. So here, my change is greater. Here, my change is less. It's not constant, as you said. But we still want to be able to deal with rates of change with graphs like this. See, we're in year 12. We're not satisfied with just saying we can't do it and let's move on. It's just too hard for us. Sometimes you've got to go towards the challenge, accept it, and enjoy it. Okay. So let's think about a specific point. Between these 2 points, we've got a certain change. If I draw a straight line between these 2 points, what's the slope of that? If I call this one, say, I call this point A, a plus h, f of a plus h. And that point there is a, f of a. So what we're saying is this point, the x-coordinate of this point is just a. So then the y-coordinate is just the value of the function at a. And then we're saying over this distance here, we've just got a distance of h. And so then this is a, just h units on. And so it's f of a plus h. How can I find the slope of that line? What would it be? Yep.
f of a plus h minus f of a over a plus h over a minus h.
So remember that slope is just rise over run. So it's just the value of the y-coordinate here, which is f of a plus h. Take f of a, the value of the y-coordinate down there, over the subtraction of the x-coordinate. So a plus h, take a. Now, that means I can take those a's away. So the slope is going to give me f of a plus h, take f of a over h. So that's kind of an approximate way of getting how my change has occurred between these 2 points. But is the graph consistent between those 2 points? Does it have a consistent change in all the values between those 2 points? Yes, no? So here, as you follow along the graph, is the rate of change always the same? Not on the curve one, which is my original graph. So this does not give me the rate of change for every point on this curve. It just gives me a general idea between these 2 points as a whole. In other words, we call it the average rate of change. It's an average idea between those 2 points. Gives us a rough idea on the change between those 2 points, but it doesn't describe the change at every one of those points along this curved line. Any questions about that? Do I need to back up and go over anything? Anybody really lost? Okay, let's keep going then. So you see, how can I get the rate of change for just one particular point? Just this point here. How can I know how much it is changing at that point? That's where a tangent comes in useful. So we draw a tangent to the curve at this point. And notice, between here and here, the curve has exactly the same slope as our straight line. There's actually no difference. So around the point of contact, the slope of the tangent and the slope of the curve is actually the same. So if we could get the slope of this tangent, that would be the rate of change of the curve at this one point. The question is how to get the slope of the tangent. Well, let's go into this diagram here. So if I start, so this is what I was talking about before. This point here has an x-coordinate of a. We go h units on, and this x-coordinate here has an x-coordinate of a plus h. And so I can draw the average rate of change. I can draw the straight line. It's a little wonky, but it'll do. And then I can bring h in. I can say, well, let's decrease h, so now b is here at this point. So then I get a line that goes down a bit. The slope decreases. And then we say, well, let's do that again. Let's bring h in so it's here. And let's draw this point, or this line. And each time the slope is coming down, it's decreasing. And so what slope is it becoming more like as it's decreasing? As it comes down, what is the slope becoming more like? The tangent. So much so that if you headed all the way, if you brought B all the way in to A, the idea is that you'd be heading to the point, as you're bringing B in, you're heading towards the point where the slope of this chord is actually going to be the same as the slope of this tangent. What that means is we can say the limit as point B heads towards point A of the slope of the chord must equal the slope of the tangent. See, as point B is going towards point A, the slope of the chord is becoming closer and closer to the slope of the tangent. And we know what the slope of the chord is. The slope of the chord is f of A plus h. Take f of A all over h. And instead of saying B goes to A, because that's pretty unspecific, well, remember the distance between B and A is h, so we can just say the limit as h goes to 0. That's going to bring B in towards A. So this must be equal to the slope of the tangent. That's where we get the first principles formula from. You should have seen this formula before. But that's where it comes from. It comes from the idea that the slope of this chord, as we draw h in towards 0, the slope of the chord is actually heading towards the slope of the tangent as h goes to 0. Now, that's for some specific point A. But if we said, well, instead of at A, I don't want to know it at A, I want to know it at any point on my curve. Then all we have to do is we just have to generalize the point A. So this gives me f dash of A. In other words, this is the slope at a point. But if I want the slope at any point, well, I don't specify the point that I'm talking about. So f dash of x will be the limit as h goes to 0 of f of x plus h, take f of x all over h. And so what will happen is we'll get an expression in terms of x here, and that will be what we call our derivative function. So the expression in terms of x is my derivative function. This gives it to me at a general point. Okay. I need some feedback on that. Is that okay for you? Okay. Right. You can talk or continue at a class talking. Yes. 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 Good. Okay. All right. It's that time. So we are 5 minutes to go. Okay. All right. Yes. I forgot about it. I got too excited. So, okay, what I'm going to say is, everybody can head off. If you already got your books, that's fine, you can go. If you don't have your books, just go over to the library and grab them. Who doesn't have their books? Okay, so you guys go up first and just grab the books. The rest of you can head off as well. I will come at you guys to go.